Hello everyone. My name is Tanu. I'm a research scholar in IIT Bombay. Here we will be having our interactive session 2 on circular dichroism and Mossbauer spectroscopy. So, in the first interactive session, we took some sample problems on symmetry and we took different examples of molecules and find out different symmetry elements in those molecules. So here we will be continuing with some more examples of symmetry to find out symmetry elements in particular molecules, and also we will be associating whether a molecule is chiral or not, and this will be associated with the type of symmetry element present in a particular group. So I'll be giving a brief summary of the main lectures, and then we will be starting. We will discuss the examples. So it's 6 2. We will wait till 6 5 p.m. so that if someone has to join, and then we will continue our session. I hope you guys are following these interactive sessions and you're also watching the lecture videos. So, if you have any doubt, please post it in the discussion forum, or you can join any interactive session. So, you can come up with your any doubt, like whatever problem you are facing with the content or anything. We will be happy to know your feedback and any suggestions to improve these interactive sessions. So, let's get started with our interactive session. A brief summary. So, what are the five symmetry elements we have discussed so far? First is identity operator. Second is rotation around an axis. That is CN operation, CN symmetry element. So whether we are rotating a molecule around 60 degree, 120 degree, 180 degree, so this rotation around an axis we define based on that, and n is equal and theta. For example, if we are rotating the molecule around C3 axis, then this n will be 3 and theta will be 120 degree. Okay, so for example, if we are rotating the molecule around 180 degree angle, then this n will be 2. So for theta equal to 180 degree, we have n is equal to 2. So this way we will find out what is the rotational axis present in a particular molecule. Then we have reflection through a plane. So we have three type of planes. First is sigma h, horizontal plane. So in a molecule, we will have one principal axis, and that will be the minimum order axis. That is the minimum angle at which we are rotating a molecule, such that we are getting an equivalent configuration. For example, if we rotate if a molecule has C2 axis also and C3 axis also. So if we rotate the molecule around 120 degree angle, then this is the minimum angle after rotation, around which we get an equivalent configuration. So the minimum rotation will give us a. Oh, sorry, I forgot to on my audio. I'm sorry. Okay, I'm repeating it again. So here I'm giving a brief summary of symmetry elements that we have discussed so far. So there are five symmetry elements. First is identity operator. That is, if we rotate a molecule around 360 degree angle, that is C1, then we are going to get an identity operator. It's just in like a unity operator, so that we are not introducing any kind of change in a molecule and we are getting an equivalent configuration. Then we have a rotation around an axis, that is Cn symmetry element. So if we are rotating a molecule, for example, around 120 degree angle, then this n will be 3. That is, we will have a C3 rotational axis. So in a particular molecule we will have one principal axis, and that principal axis will be the axis around will be the minimum rotation around which we are getting an equivalent symmetry. For example, if a molecule has a C3 rotational axis also and C2 also, then the principal axis will be C3, because around the minimum rotation, that is 120 degree as compared to 180 degree, we are getting an equivalent configuration. That is uh, we are getting an equivalent configuration, so that will be the principal axis. Then we have reflection through a plane. So we have three types of plane: sigma h, that is horizontal plane. Then we have vertical plane, sigma v, horizontal plane, vertical plane, and then dihedral plane. So for a particular molecule, we have only one principal axis, and this horizontal plane is always perpendicular to the principal axis. Rushikesh, you have started presenting. Uh, can you please stop it? Just a minute. Rushikesh, can you stop presenting? I have not put a restriction on this, so the lecture is getting disturbed. Can you hear me? So I haven't put any restriction on this sharing part. So please don't interrupt the lecture in between. Like, don't share and all of these things. So we were discussing about horizontal plane. So with respect to a principal axis, we have only one horizontal plane in a molecule, which will be perpendicular to the principal axis. Plane perpendicular to the principal axis. Then we have vertical plane. So we can have more than one vertical planes in a molecule. So whichever plane which contains the principal axis on it will be a vertical plane in a molecule. So we can have one or two or three, any number of vertical plane in a molecule. For example, we have C3 principal axis, so we will have corresponding n sigma v in a molecule. That is, if it is C3. So if we have C3, then we will have 3 sigma v plane in a molecule. So if we have one vertical plane, then we will have corresponding three. There must be three vertical planes corresponding to a molecule. Otherwise, we won't have any vertical plane. So we will have n sigma v vertical plane either in a molecule or no sigma v. Then we have this dihedral plane, which is the plane which bisects the C2 axis, which are perpendicular to each other in a molecule. So next is reflection through a point. That is inversion center. This is basically center of symmetry. So if we do a reflection around this center of symmetry and we are getting an equivalent configuration, then we can say that we have an inversion center in the molecule. Then the last one is improper axis of rotation. So operation, this symmetry element involves two operations. First is rotation around an axis, and then inver- uh, followed by a reflection through a perpendicular plane. That is reflection around an axis, followed by this is rotation around an axis, followed by reflection through a plane perpendicular to this CN axis. So these are five type of symmetry elements, and we can group them into different point groups, and based on some mathematical rules, and we can find out to which molecule a particular sorry to which group a particular molecule belongs to. So E, Cn, sigma H, Cn, and I. These symmetry elements are grouped based on some mathematical rules to get point groups. And these symmetry divisions by group is of four types. So first we have non-rotational groups. That is, we don't have any rotational axis in that molecule. So these groups are CS, Ci, and then C1. So here we will have only sigma plane in that molecule. That is, we only have a plane in that molecule. Here we will have only inversion center, and this is basically kind of, here we will have only identity operator in that molecule. Then we will have single axis rotation groups, which are Cn, Cnh, Cnv, S2n, and C infinite V. Then we have dihedral groups, Dn, Dnh, Dnd, and D infinite H. And then we have high symmetry groups, which are octahedral and tetrahedral group. So now we know that we have four kind of groups, but how will we figure out the type of group a molecule belongs to? So there is a flow chart, a summary of all these groups, and here you will be following some rules, like you will be finding out with respect to a particular symmetry element uh, which group a molecule belongs to. So firstly, you have to find out the molecular structure of the group of the molecule. Sorry. First is the molecule linear? So if the molecule is linear, the next question we have to ask is whether the molecule is linear or not. Based on that, if the molecule is linear, then we will find out whether it has inversion center in it. If yes, then it will belong to D infinite H point group. For example, CO2. If we have if we don't have inversion center, then it will belong to C infinite V. For example, so for linear molecules, these are the 2 point groups which we can find out, that is D infinite H and C infinite V. If a molecule is linear and then it has inversion center, for example CO2, then it belongs to D infinite H point group. Otherwise, it will be C infinite V. So if a molecule is not linear, then the next question we will ask is whether belongs to special symmetry group. And the special symmetry groups are high symmetry groups, which are octahedral and tetrahedral point groups, that is molecules with cubic symmetry. So special symmetry group, if yes, then we will have to find out whether it is tetrahedral or octahedral. So these are special cubic groups. If not, the next question we will ask is, these molecules are not linear and they don't have, then they are also not high symmetry groups. So the next question should be, what is the rotational axis present in the molecule? Does the molecule have a rotational axis present in it? If no, then we will ask whether it has a plane, like any plane present in it, because we will specify whether a molecule has horizontal, vertical or dihedral plane based on the rotational axis, based on the principal rotational axis. But if we don't have any rotational axis in the molecule, then we will just find out whether a molecule is has a plane which is bisecting it into an equivalent configuration, bisecting in such a way that we get an equivalent configuration after it. So if a molecule has a sigma plane, then it will belong to CS point group. So, and if not, then we will again ask a question whether it has an inversion center or not. If yes, then it will belong to CI point group, and if not, then it will belong to C1 point group. So these are non-rotational point groups, CS, CI, C1. So here we will only, if a molecule has only sigma plane or only inversion center, or none of these, then it will belong to non-rotational groups, which are CS, CI and C1 respectively. What if we have a rotational axis in the molecule? So the next question we will be asking is whether the molecule has NC2 perpendicular to this principal CN axis. If no, if it doesn't have n, so if say for example, if we have a C3 axis, so here there is a one condition: this principal axis must be n greater than 2, that is, it should be C3, C4, C5, C6. And then if it is, for example, C3, then it will have 3 C2 perpendicular to that principal axis, or it will not have any C2 perpendicular to it. Either it will have one, or it will have corresponding n C2 perpendicular to that principal axis. So if we don't have NC2 perpendicular to CN, then we will ask whether we have an horizontal plane perpendicular to this principal CN axis. If yes, then the molecule will belong to CNH point group. And if no, the next question we will be asking is whether it has N sigma V planes. So as I said, either the molecule will have n sigma v corresponding to the Cn principal axis, or it will not have any vertical plane in it. So if it has n sigma v, then it will belong to CNV point group. And if it doesn't have any vertical planes, then the molecule will belong to simple CN point group. So these are single axis point groups. That is, here we have only one rotational axis, which is principal axis. What if we have NC2 perpendicular to the principal axis? So again, here we will be asking these questions: whether the molecule has sigma h, that is perpendicular horizontal, that is a plane perpendicular to the principal axis. If yes, then the molecule will belong to DNH point group. And if not, then it will have, then we will be asking whether it has n sigma d dihedral planes. That if it has any plane which is bisecting these C2 axis perpendicular to the principal axis. If yes, then we will have DND point group. And if not, then it will be DN point group. So these are dihedral groups. So this is a simple summary of how we can find the different symmetry elements in a particular group, and then we can group them into different point groups, which are D infinite H, C infinite V. Then if it is linear, then we have D infinite H and C infinite V point groups. If it is not, then we will find out whether it belongs to special symmetry groups, which are tetrahedral and octahedral. And one thing we have to make sure of, that we don't have to look into the coordination geometry. We have to look into the symmetry of for example, octahedral symmetry and octahedral coordination geometry is different. A molecule might have an octahedral geometry, but it might not have this octahedral symmetry. So that we have to be very careful about. And if it doesn't belong to special symmetry groups, then it means it belongs to lower symmetry groups, which are CS, where we have only sigma plane in the molecule, Ci, where we'll have only inversion center, or we won't have any rotational axis, any plane or inversion center in the molecule, then it will belong to C1 point group. if it has more number of like more, other than principal axis, if it has other rotational axis, for example C2, then it will belong to single axis rotational groups, which are CNH, CNV, CN. And if it has uh, if sorry here I said if it doesn't have NC2 perpendicular to CN, then it will belong to single axis rotational groups. And if it has more rotational axis other than principal axis, then it will belong to DNH, DND, DN dihedral groups. So this was the brief summary. Now we will start taking some examples. If you have any doubts related to this, you can ask me. Okay. So here we will start with some examples. So first example I am taking is Genon OF4. So, firstly, you have to be very careful about drawing the geometry of a particular molecule. If you're drawing a incorrect geometry, then you might land up in a wrong point group. That you might guess, you might be guessing a wrong point group for that molecule. So, for this, you have to brush up your chemical bonding concepts. So, make sure you draw the right structures. So, here we have Genon OF4. So this is square pyramidal geometry. So the first question we will ask is, whether the molecule has linear geometry or not. So we can see that molecule belongs to square pyramidal geometry. So the molecule is not linear. Now the next question is, does this molecule belong to special point groups? Does this molecule belongs to special symmetry point groups? So it doesn't have any tetrahedral and octahedral geometry. So firstly we will see that the molecule will have tetrahedral and octahedral geometry. That is sure. But even if a molecule has tetrahedral and octahedral geometry, then it doesn't mean that it will have tetrahedral symmetry point group and octahedral symmetry point group. So this molecule doesn't belong to special symmetry groups. The next question is, does it have a principal axis, a rotational axis? So yes, this molecule has C4 axis passing through this Genon double bond O. So this double bond O is out of plane and these five atoms are in plane, and this double bond O is perpendicular to this Genon and these four F planes. So it looks like this here we have one fluorine, two fluorine towards you, and two fluorines away from the observer, and this double bond O is perpendicular to this plane. Let me represent it like this. And this C4 axis is perpendicular to this plane. Okay, now we have, yes, we have Cn axis, and that is C4 axis. So that if we let me represent this C4 axis. If I label these fluorine atoms, one, two, three, four, and I apply this fourfold axis of rotation operation on this molecule, then we will get this configuration. We will be rotating it at 90-degree angle. C4 is nothing but 360 degree divided by 90 degree. So here n is 4. So we will be getting this configuration. So this is an equivalent configuration. So this is how we will after this 90-degree axis 90-degree rotation, this is the equivalent configuration we will get. Okay, so now the next question we will be asking is whether we have nc2 axis perpendicular to this c4, and so here n will be 4. So do we have 4 c2 axis perpendicular to c4? I'm drawing this structure again. So here we have this C4 axis perpendicular. So what are the possible C2 axis perpendicular to this? We can have this C2 axis. So if we rotate this molecule at 180-degree angle along this rotational axis, so the configuration we will be getting is F3. So these two configurations are not equivalent. That is, these are not superimposable. This is not an equivalent configuration. Instead, we are getting an inverted configuration. So this molecule doesn't have a C2 axis perpendicular to C4 principal axis. So molecule doesn't have 4 C2 perpendicular to C4. The next question we will be asking is whether the molecule has an horizontal plane. So the perpendicular to this perpendicular to this C4 axis, we have this plane which contains this genus and these four fluorine atoms on it. So if we apply this horizontal plane, then we will again getting this inverted configuration. So this molecule doesn't have an horizontal plane because we are not getting an equivalent configuration, identical configuration. So molecule doesn't have horizontal plane. So the next question we will be asking is whether the molecule has 4 sigma V. So yes, the molecule has 4 sigma V, 4 vertical planes. And what are these planes? So this is one sigma V plane. Then we have this sigma V plane. This plane will contain this gene and double bond O on it. All vertical planes will contain the principal axis on it. So this is sigma V. Then we have 2 sigma V which are passing through these F1G, these fluorine gene and F fluorine bonds. So here we have 4 sigma V in the molecule. Therefore, the molecule belongs to C4V point group. Okay, so this is how we will be mapping to what point group a particular molecule belongs to. This way you will not be forgetting any symmetry element present in that particular molecule, and then you will be able to group them into a point group. So it will be easier for you when you follow this flow chart. Okay, and here I forgot to mention this new concept taught in the main lecture, which is that of chirality. So let me mention which molecule is chiral and which molecule is not. I'm just summarizing it here. Concept of chirality. A molecule can't be chiral if it possesses SN axis of rotation. That is, if it has an improper axis of rotation in it. So firstly we will have to find out the point group of the molecule, and then we have to check whether it has SN, that is improper axis of rotation. So the point groups which are considered to be chiral because they don't possess any improper excess of rotation. Chirality are Cn and Dn point groups. If a molecule belong to these two point groups, then the molecule will be chiral. Otherwise, molecule will be achiral. So here, this Genan OF4 molecule belongs to C4V point group, which shows that it doesn't belong to uh, it is not a chiral molecule. 4 doesn't belong to chiral point groups Cn and Dn. Therefore, it is a chiral. So the next example we are taking is that of allene. So we have to find out these two hydrogen bonds are in plane of the board, and this hydrogen is out of plane out of plane and towards the observer. This is also out of plane and away from the observer. So we can represent this allene if we consider that we are observing this molecule from here, observer. Okay, so here these two hydrogen atoms I'm labeling as 1, 2, these are 3, 4. So if I'm observing this molecule, for example, these two hydrogen atoms are in front of me, so I'm drawing it as like this. And these hydrogen H3 and S4, one of them S3 is right hand side and S4 is left hand side. So and it is away from the these are away from the observers. So taking it as S3 and H4, like this. So, first question we will be asking is whether the molecule is linear or not. So, the molecule is not linear because these hydrogen atoms are not in uh, are not in one single line, and these two hydrogen atoms are out of plane. Okay, so the molecule is not linear. The second question is, does it belong to special symmetry group? No. Special symmetry group? No. Then the third question is, does the molecule have proper axis of rotation? So if we see here, if we rotate this molecule at 180-degree angle, there are different C2 present in this molecule. So one is here, C2. Then we have, so here we have three C2 X's in this molecule. So yes, the principal axis is C2. Then we have two C2 perpendicular to the principal C2 axis. Yes. The next question we are asking is whether the molecule has horizontal plane. So here I'm drawing it again. So in this molecule, we have dihedral planes. We have planes which are bisecting these perpendicular C2 axes. One is the molecular plane, that is plane of the molecule. You can consider it as the plane of the board also, molecular plane, which is dihedral plane because it is bisecting these C2 axis, these perpendicular C2 axis. So one plane contains these two hydrogen atoms on it, and one plane contains these two hydrogen atoms on it. So these are two dihedral planes in this molecule. So we don't have an horizontal plane. Yes. So this alene molecule belongs to D2D point group, and hence it is a chiral. Now, if we substitute one of the hydrogen atoms with any other functional group, let's say methyl group, so what will be the symmetry of that particular molecule? Will it be still a chiral, or it will change into a chiral molecule? So let us see. I am substituting one of the hydrogen atoms, which is in the plane, with a methyl group. This is the molecule we will get. And if we draw it, will look like this. And here we have H A and H B. So now we have to see firstly that the molecule is again not linear because we have already checked, because these hydrogen atoms are out of plane. This molecule is totally not linear, that all the atoms are in one line. Okay, then we will be checking out whether it belongs to a special symmetry point group. Again, it is not octahedral or it doesn't have an octahedral and tetrahedral geometry, so that option is ruled out. Then we will check whether the molecule has a principal axis of rotation, principal, or we will only, like, we will check whether the molecule has an axis of rotation. So here, after introducing this methyl group, we can see that we don't have any any axis of rotation in the molecule. So first, molecule is linear. No. Second, special symmetry point group, tetrahedral or octahedral. No. Then Cn, that is uh, what is the axis of rotation present in the molecule. So it doesn't have Cn axis. Fourth, we will check whether the molecule has any plane in it. So yes, this has one. So yes, this molecule has one plane, which will contain this methyl and hydrogen group in plane on plane, and these two hydrogen atoms which are out of plane will be reflected through this plane. Okay. So yes, it has molecular plane. So the molecule belongs to CS point group. And this molecule is a chiral. Since it doesn't belong to a CN and DN point group. Okay. So now again we will be doing some changes in this alene. We will be substituting two hydrogen atoms with chlorine atoms. One hydrogen atom which is in the plane and one which is out of plane. And then we will find out what will be the what will be the symmetry elements in that molecule and to which point group it belongs. Let's say if we have C chlorine atom instead of hydrogen atom. Okay. And if we represent it as Cl, so now we have to find out whether again this molecule is not linear and doesn't belong to any special symmetry point group. So we will have to find out whether this molecule has a rotational axis in it. I've done a mistake here. So here we have one C2 axis which is passing through this central carbon atom and is aligned at 45-degree angle with respect to these chlorine atoms. This is the C2. So here we have C2 rotation, rotational axis. Now the next question is, do we have two C2 perpendicular to this C2 principal axis? No, we have only one C2 axis in this molecule. Now the next question is, does the molecule have an horizontal plane? So perpendicular to this C2 axis, we have this molecular plane. So by molecular plane, I mean that this plane of the board and the plane which is containing the most of the atoms on it. So these hydrogen and Cl atoms are outside this molecular plane. And if you bisect this molecule through the molecular plane, then these hydrogen and chlorine atoms will exchange the positions and we won't get an equivalent configuration. That means we don't have a horizontal plane in the molecule. Now the next question is: Do we have any vertical planes in the molecule? So again, we don't have any vertical planes. For vertical planes, it should be like we should have a plane which contains this C2 axis on it, but after bisecting this molecule along this vertical plane, we won't get an equivalent symmetry. We will be getting these hydrogen and chlorine atoms being exchanged being exchanged on their positions, and this will not be an identical configuration, so we don't have any vertical planes in the molecule. So here it means the molecule belongs to C2 point group. That is, it belongs to single rotational axis group where it doesn't have any vertical plane, horizontal plane or any inversion center. So this molecule is also chiral because it belongs to Cn and Dn point group, that is C2 point group here, and hence the molecule is chiral. And hence the molecule is chiral. So you can see how substitution of these atoms with different molecule different substituents, we are getting a change in symmetry, and based on that the molecule is changing from a chiral to a chiral molecule. Okay, so this was an example of how we can find out a molecule belongs to chiral and a chiral, whether a molecule is chiral or achiral based on its point group. The next question is, we have PBrCl4. So firstly you have to find out the correct structure of the molecule. So here the molecule has this structure. So why I haven't placed this bromine atom on the equatorial positions? So again, it depends on these chemical bonding rules, where you will see that heavier atoms will be, that is sterically, this bromine is heavier than chlorine atom, and this will have steric hindrance on the molecule. So we put it on the axial position, so that in a molecule we have minimum steric hindrance. So here this molecule has trigonal bipyramidal geometry, and these three chlorine atoms are on a plane, and these chlorine and bromine atoms are above this plane and below the plane. Okay, so the first question is again whether the molecule is linear or not. So the molecule is not linear, then it doesn't belong to octahedral and tetrahedral geometry. So special symmetry group, no. Then we have to find out whether the molecule has a rotational axis. So we will be finding the proper axis of rotation in the molecule. So here we have C3 axis of rotation in this molecule, such that these three chlorine atoms, which are at 120-degree angle with respect to each other, so when we rotate this molecule at this C3 axis perpendicular to the plane in which these three chlorine atoms are contained, we will get a configuration like this. This Cl and this bromine will remain on their position, that is, there will be no change of positions. But here, these chlorine atoms will change their positions because they are at 120-degree angle with respect to each other, and we are rotating this molecule at a 120-degree angle. So here we will get a configuration like this. So these two configurations are identical. Okay, so we have C3 axis of rotation in the molecule. Now the next question is, Do we have three C2 axes perpendicular to the principal C3 axis of rotation? So no, we don't have any C2 axis because perpendicular to C3 axis, let's say we have, just a minute. So let's say if we have this C2 axis passing through this PCl bond and we rotate this molecule around this C2 axis, then we will get an inverted configuration. That is, this Br and Cl will exchange their positions and we won't get an identical configuration. So we don't have a C2 configuration, the C2 axis of rotation in the molecule. Then we will be asking whether the molecule has an horizontal plane. So again, the only plane perpendicular to the C3 axis is this plane which contain these three Cl atoms and this phosphorus atom. So if we reflect the molecule along this horizontal this plane, then this chlorine and bromine atom will change their positions. So we don't have a horizontal plane in the molecule. Next is, do we have 3 sigma V in the plane? So yes, we have 3 sigma V in the plane. There will be 3, just a minute, P, Cl, Br, Cl. So there will be 3 sigma V planes passing through each phosphorus chlorine bond, and they will be containing this bond on it. Okay, so yes, we have 3 sigma V planes in the molecule. Yes. So the molecule belongs to C3V point group, and hence it is a chiral. Okay. The next example is that of dinitrogen dihydride. So you might be thinking that this molecule is similar to S2O2, but here if you but here we have these nitrogen atoms are sp2 hybridized. So these two hydrogen atoms were out of plane, but these hydrogen atoms are on the molecular plane. Okay, so this had an open book structure. But here this is not the case, and these hydrogen atoms are lying on one single plane. So firstly, the molecule is not linear, no special symmetry point group. So I'm just writing octahedral or tetrahedral. No. Then what is the rotational axis present in the molecule? So here we have C2 axis in this molecule. Okay, C2 axis. Then do we have two C2 perpendicular to this C2? So the possible C2 are perpendicular to this C2 axis. So we don't have any other C2 axis in the molecule. No. Then do we have horizontal plane in the molecule? So yes, this molecular plane contains all these nitrogen, two nitrogen and hydrogen atoms on it, and this molecule is perpendicular to this C2 axis. So yes, we have an horizontal plane in this molecule. Therefore, this molecule belongs to C2H point group. And also here in this molecule, we have an inversion center present. Okay. So if you reflect this molecule around this point, so you will see that there is a hydrogen atom opposite to each other at equivalent at equal angles, and nitrogen atoms opposite reflecting each other. So we have inversion center also in this molecule. So this molecule is has C2H point group and is not chiral. Okay. Now the next question is this molecule. So first, the molecule is not linear, tetrahedral or octahedral. No. What is the principal axis of rotation present in this molecule? So here in this molecule, we have a C4 axis of rotation perpendicular to this ring cyclobutane cyclo perpendicular to this ring, and these OH groups will move accordingly, and we will get an equivalent configuration. Okay. Then do we have 4C2 perpendicular to this C4? So if you consider that there is a C2 axis perpendicular to this C4 axis, okay, and you rotate this molecule. So after C2, you will get a configuration like this, and this is not an identical configuration. So we don't have 4C2 perpendicular to this C4 axis of rotation. Then do we have sigma h horizontal plane in the molecule? So yes, we have a horizontal plane in the molecule, which is this molecular plane. Therefore, this molecule belongs to C4H point group. Hence, it is not chiral. So you just have to find out the symmetry elements, and then to what point group these symmetry elements belong to, and then you can comment on the chirality of a molecule. Now the next example is staggered ethane. So if you draw this uh, Sawhorse projection of staggered ethane, it looks look like this, and this is the Newman projection. If the observer is here, H4, H5, and H6. So now the first question is, molecule is not linear, not tetrahedral, octahedral. No. So what is the principal axis of rotation present in the molecule? So we have C3 axis of rotation. Just a minute. I just need a 2 minute break. So here we have C3 axis passing through this center of the molecule, and these hydrogen atoms will be rotated at 120-degree angle with respect to each other. So we have C3 axis of rotation. Then do we have three C2 axis perpendicular to this C3 axis? So yes, we have C3 C2 axis perpendicular to this, which will be passing between these bonds. Okay. So next is, do we have horizontal plane? So yes, we have horizontal plane. No, we don't have horizontal plane. Then we will check, do we have any uh, dihedral planes, because we have three C2 perpendicular to each other. So we will have we will have dihedral plane instead of vertical planes now. So yes, we have dihedral planes in the molecule, which are again containing these C2 axis, such that it is bisecting the molecule at angle, such that other two C2 axes are perpendicular to each other. So yes, we have three sigma dihedral planes in the molecule. So this molecule belongs to D3D point group. Okay, hence it is a chiral. Next we have 135 trichlorobenzene. 135 trichlorosubstituted benzene. So the first question is whether the molecule is linear. No. Any special symmetry point group? No. Then what is the principal axis of rotation? So here we have C3 axis of rotation, such that if you rotate this molecule at 120-degree angle, it is perpendicular to the plane of ring. You will get an identical configuration. Okay, so we have C3 axis of rotation. So do we have 3 C2 perpendicular to this C3 axis? So yes, we have 3 C2 axis perpendicular, which is passing through each of these Cl bonds. So yes, then the next question is, do we have an horizontal plane? So yes, the molecular plane, that is which is containing this benzene ring and these chlorine atoms on it, it is perpendicular to the C3 axis, so it has horizontal plane. Therefore, this molecule belongs to D3H point group. Hence, it is a chiral. And a few other examples which are similar to this are that of BF3, which is a very basic one for molecules with this D3H point group. Then we have this N3P3 Cl6 molecule. Then we have cyclopropane ring. So these molecules have D3H point group. Similarly, we have this bicyclo 1,1,1,1 pentane. This is bicyclo 1 pentane. So these molecules have D3H point group. Similarly, PCl5 also has D3H point group. So now let's take an example of D4H point group, which is bicyclo 110 butane. So it is equivalent to, so here we have C2 excess. Sorry, this is not an example of D4H point group. I'll show it later. So this has C2 axis perpendicular to the molecule, special group. No. Then we don't have any C2 axis perpendicular to this. So we have only one C2 axis. Then we don't have any horizontal plane in the molecule. We do have two sigma V planes in the molecule, which is one is this sigma V, and then another is horizontal plane, that is, sorry, molecular plane of this board. Therefore, we have two sigma V. So this molecule belongs to C2V point group. Some other examples are water, OCl2, etc. Okay. So now a few examples of D4H point group are PTCl4. So this is the top view. The side view will look like this. Okay. And we will have a C4 axis perpendicular to the molecule. Then we will have a horizontal plane which is perpendicular to this C4 axis and containing all the atoms on it. And then we will have four C2 axes. also we will have 4 sigma V. So this is the D4H point group example, and other examples are cyclobutane. Okay, and then the few example of D6H point group are benzene, D5H, okay, then D and D dihedral point groups. This is basically kind of a lean type of molecules. Okay, then we have already seen an example of staggered ethane, which belong to D3D point group. Then we have this metallocene, which is an example of D4D point group. So we have already discussed a lot of examples on these point groups. So by now you are able to find out how can you map out the different symmetry elements in a molecule and connect it with a particular point group. And then you can also assign the properties, certain properties, such as we have taken the example of chirality for now. We will be further discussing like optical activity, polarity, etc. in further lectures. Okay, and um, let me show you an example of dn point group, which is COEN3 2 plus. So en is ethylene diamine. So here, firstly, the molecule is not linear, doesn't belong to any special symmetry point group. No. What is the proper axis of rotation present in this molecule? So here we have C3 axis of rotation present in the molecule, such that if we 1, 2, 3, 4, 5, 6, if we rotate this molecule at 120-degree angle, 4, 5, and 6, this N3 is connected to N5, N2 is connected to N4, N1 is connected to N6. So here you can see clearly we are getting an identical configuration. If you label these atoms and you move it like uh, if you move it and rotate it in 120-degree angle, so you will find out we will be getting an identical configuration. Okay, so here we have C3 axis of rotation. Now, do we have 3C2 perpendicular to this C3? So yes, we have C2 axis passing through the center of these ethylene diamine bonds. So these are the three C2 axes present in this molecule. Now the next question is, do we have an horizontal plane? So if this C3 axis which is coming out of plane, and if we bisect the molecule, then we won't get an equivalent configuration. So we don't have an horizontal plane in this molecule. Therefore, this molecule belongs to D3 point group, and hence this molecule is chiral. Molecule is chiral. So these were the examples I have taken today. So I hope you were able to understand these examples. And if you have any doubt, you can ask me in the next session. And also, whoever is present in the meeting, uh, let me check. Okay. So we have only one participant now. Do you have any question, Anita?
Ma'am, no, ma'am.
Okay. Uh,
Ma'am, but I need a clarification.
yes.
Ma'am, I had enrolled in this course 2 days back. Can I able to join with the lectures and the courses hereafter?
Yes, yes, you can follow the previous lectures also. When you will log in into the SWAM portal and this course, Circular Dichroism, you can see the video lecture of last 2 weeks also. But you might not be able to submit the assignment which have been uploaded in the last 2 weeks. Okay.
Okay, ma'am.
Okay, and these interactive sessions were a brief summary of last two sessions. So if you want to follow the this session, you will be able to find out like what has been taught so far, and you can follow the main lectures also.
Okay, ma'am. Thank you, ma'am.
So this is it for today. I hope I could solve your doubts, or these examples will be helpful for you to solve the assignment. If still you have any doubt, you can ask me in the next session also, or you can post in the discussion forum. Okay? Okay. So thank you so much. I'm ending this meeting for today.